I want you to picture a blacksmith's forge. You can almost feel the heat, smell the smoke, hear that loud clang of a hammer hitting glowing iron. It's a scene that's been around forever. But a simple question from a student named Anandi is about to turn this whole ancient craft into a science lesson, one that reveals the huge difference between two major types of materials that make up our world. Why are you beating it? It seems like such a simple question, but the answer? It's profound. The blacksmith isn't just whacking a piece of metal to make an axe. He's actually showing us a core property that splits the material world into two big groups, the stuff we build our world with, and the stuff that, well, builds us. So, what's the blacksmith's big secret? It's not just about being strong or being able to take the heat. It's really about how a material reacts when you apply force to it. And this one powerful idea, it's our very first clue in figuring out the massive difference between metals and nonmetals. And that secret, it has a name: malleability. It's the amazing ability of a material to be hammered or pressed into thin sheets without just shattering. It's how that big lump of iron becomes a sharp axe, and it's the very same reason you can wrap your leftovers in aluminum foil that's thinner than paper. Okay, let's do a little thought experiment here. Imagine you take a hammer and you whack an iron nail. What happens? It flattens out, right? But now, what if you hit a piece of coal with that same hammer? It just shatters into a bunch of little pieces. And that right there is the difference. The iron is malleable. The coal is what we call brittle. It's the total opposite. All right, so think of this as a showdown. Malleability, just one round one for the metals. But there are a bunch of other key differences that really separate these two teams. Next up in the showdown, we have ductility. Now, this is the property that lets a material be stretched out into a thin wire without snapping. Just think about it for a second. Every single electrical cable running through your walls, the strings on a guitar, they all exist because metals like copper and aluminum are so ductile. And if you want to know just how extreme this property can get this. You can take a single gram of gold that's tiny and draw it out into a wire that's 2 kilometers long. That's insane. That incredible flexibility is exactly why it's so perfect for making delicate jewelry. All right, now for a property you can actually hear. It's called sonority. It's that special ringing sound something makes when you hit it. Just imagine the sound of dropping a set of keys on the floor versus dropping, say, a block of wood. That difference you're hearing, that's sonority in action. So metals are sonorous. A metal spoon makes that distinct ring when you drop it, but a wooden one just makes a dull thud. This is exactly why things like school bells, cymbals, and those gungrus, the little bells dancers wear, are all made out of metal. They're literally designed to make that clear, ringing sound. Okay, here's one more quick experiment you can just picture in your head. Take a metal spoon and a wooden spoon and stick them both in a glass of really hot water. Now, you wait a couple minutes. Which one do you think is going to be hot to the touch at the end that's sticking out of the water? I'm guessing you already know the answer, right? The metal one gets hot. But why? Why does one get hot and the other one doesn't? Well, it points to another huge, fundamental difference between them. The metal spoon gets hot because metals are fantastic conductors of heat. That heat energy just zips right up the spoon. Wood, on the other hand, is a poor conductor. It's an insulator. And you see this in your kitchen every day. Your cooking pan is metal so it can get heat to your food, but the handle is wood or plastic to keep your hand from getting burned. Okay, so we've hit them, we've stretched them, we've heated them. But what happens if we just leave them out in the open? Let's switch gears from physical properties and start looking at chemical reactions, specifically with two things that are all around us all the time: air and water. We've all seen rust on an old gate or a tool left outside. But what's really going on there, chemically? Well, for rust to happen, you need both air and water. It's a team effort. If you keep iron totally dry or put it in water that has no oxygen, it just won't rust. It's a very specific chemical reaction with its environment. And this leads us to a really deep chemical divide. When things react with oxygen, they make something called an oxide. And here's the cool part. Metal oxides are usually basic. That means they'll turn red litmus paper blue. But non-metal oxides, they're acidic. They do the opposite, turning blue litmus paper red. It's like a fundamental chemical fingerprint for each group. So we've got our rules down right. Metals are hard, shiny, malleable things that conduct heat. And nonmetals are pretty much the opposite. Seems simple enough. But, science is almost never that simple. The world of materials is full of some really cool exceptions and some serious unsung heroes. So let's meet some of these rule breakers. We tend to think of metals as being really hard and solid. But then you have sodium and potassium, which are so soft you can literally cut them with a butter knife. And then there's mercury, the only metal that's a liquid at room temperature. You might have seen it in an old thermometer. These exceptions just go to show you how diverse even one group can be. Metals might build our cities and our cars, but non-metals, they build us. The oxygen we're breathing right now, a non-metal. The carbon that makes up pretty much all life on Earth, a non-metal. The nitrogen that helps our food grow, the chlorine that keeps our water clean, they're the invisible, unsung heroes of our actual existence. Wow. So we started this journey at a blacksmith's forge, and now we're talking about the very air we breathe. Let's pull this all together and see how this ancient understanding of materials didn't just build the past, but is still shaping our world and our bodies today. I mean, just think about the power you have when you truly master these properties. Take the Iron Pillar of Delhi. It's been standing there for over 1,600 years, and it has barely any rust on it. Now, that's not magic. It's a masterpiece of ancient science. The people who made it created this unique iron alloy that could basically defy the elements for centuries. Absolutely incredible. So when you boil it all down, our civilization really stands on two pillars. On one side, you have metals. They give us the framework, our buildings, our technology, our tools. But on the other side, you have non-metals, which provide the actual foundation for life itself, our air, our food, our health. You really can't have one without the other. So the next time you see a rusty gate, or flip on a light switch, or just take a deep breath, you'll know there's some deep science happening right there. Metals built our world, but non-metals built our bodies. And that kind of makes you wonder, doesn't it? What other essential, invisible materials are shaping your life right now?